Hello everyone, welcome to this introduction video to our course Single Variable Calculus and Analytical Geometry 1. I'd like to start the semester with a little story of what it is we are studying here. This has been developed over a long period of time, stretching back thousands of years, and it has developed into a very important dynamic study of systems. We can now, with the use of calculus, we can study systems or phenomena that change over a continuum. Usually we think of this in construct of something that changes with respect to time. So, for example, the position of an object that is moving, we can discuss its motion in a very dynamic sense, like watching a movie through the use of calculus. In the same way that when you look at a film, if you remember the old school film reels that are long stretches of film that have many photographs that go by in such at such a speed that to the viewer it appears that the images are in fact moving. But at any time, we could freeze the frame and look at a still photograph. The analysis of a still photograph, by analogy, would be like using algebra in mathematics. So algebra is very useful for talking about static phenomena, something that is not moving. But once you start putting things in motion to discuss how things change or evolve or grow or progress, okay, the ability of calculus to describe that change, okay, really becomes valuable to the observer. The roots of the study of what came to be known as calculus include contributions from the ancient Greeks, such as Archimedes, as well as Europeans, Galileo, Copernicus, Newton, Leibniz. Newton and Leibniz are often given credit for a lot of the development of calculus and the notation that we end up using. We'll be using both Newtonian and Leibniz notation in this course, for example. But also credit must be given to Chinese mathematicians and in India, where more than 200 years before Newton, they were already talking about sequences and infinite series to a certain extent. Okay? So the notion of, or the idea of the sequence and the limit are actually go back quite far in time. Okay, but we don't need to get deep into that. Okay, but let's just put down here on paper, of these four main topics that I want to discuss here in this introduction, what are they? A sequence you might have been introduced to in a previous course, such as pre-calculus. A sequence is an ordered set, okay, an ordered set of objects. So a set is a collection of elements. Those elements could be numbers, okay, for example. And if they are put in a particular order, we call that ordered set a sequence. Okay? So an example of a sequence, let's say I write the numbers 0.9, 0.99, 0.999, etc. So the three-dot ellipsis is saying that the pattern will continue, okay, as it has already been demonstrated here. And the pattern is that the next digit, okay, we're going to go out to 4 decimal places next, right? And the next digit is again going to be a 9. These numbers I'm now putting into a particular order. I have selected the first number here, okay, the first number here to be the first number in the sequence. I'm going to call it A1. So A1 is equal to 0.9. The second number in the sequence, I'll call it A sub 2, 0.99. And the third number in the sequence, I'll call it A sub 3. And so on and so forth. So that we could say that the nth term in this list, okay, the nth term in this list would be a sub n. And so the sequence is going to be defined generally by the term a sub n. And you can think of that as a function output, where the function is called a, and the input to that function, instead of being x, the input is n. If x were used, usually when we use x as the input, we imply that x is a real number, which includes positive numbers, negative numbers, but also fractions and decimals and irrational numbers, and 0. When we say n is the input, we usually mean that the input is a natural number or a counting number. So numbers like 1, 2, 3, 4, 5, so on and so forth. So the idea is, for instance, when I write a sub 1, it's like saying that there is a function such that when you input 1 into that function, the output would be 0.9. And when you input 2, the output would be 0.99. Now, if we take these same numbers, but scramble them up, that is, change their order and then retitle them with an A1, A2, A3 in a new order, we have changed the sequence because we have changed the order of the numbers. Now, this particular sequence, because it is in this order and it is constructed in this fashion, okay, it looks to us like if we were to continue out into this sequence, we would be approaching a finite value. All right, we notice that if you keep adding a 9, and so on and so forth, with each successive addition of another 9, another digit 9, we are getting closer and closer from below to the value 1. In other words, we can choose any value, we can choose to stop at any value within the sequence, and we can find the difference between that value and 1. And the further out in the sequence we go, that difference is going to get smaller and smaller. So we would notice that if we stopped at the first term even, at a sub 1, the magnitude of the difference between a1 and 1, the perceived value that we are getting closer and closer to, right, that would be what, 0.1. The absolute value of a sub 2 minus 1, that would be 0.01. The absolute value of a sub 3 minus 1, that would be 0.001. Right? And so on and so forth. Okay? And so what we are finding here is that the difference between any value in the sequence and the value that the sequence seems to be approaching, that difference gets smaller as the input gets larger. Right? So we might say that a sub n, in general, the nth term in this sequence, seems to be approaching 1, and it gets closer and closer to 1 as n, the input that tells us where we are in the list, is approaching infinity. Okay? We've set these up in a particular order, creating this sequence as an ordered set of these values, and it seems that these values are approaching 1 and they get closer to 1. The difference between the output in the sequence and 1 is smaller and smaller as the input were to increase, as we were to make some modification to the input. Okay? That idea of getting closer and closer to some value by modifying the input is known as a limit. So a limit can be described as a value that is approached by a sequence, okay? And a sequence is also a function, so it's a value that is approached by a sequence or a function, okay? In this sense, that what we mean by approached is that we can get as close as we want to that limit value, as close as we want, without actually having to reach the value. Okay? It's approached by a sequence or a function, okay, but not necessarily reached. Okay? Not necessarily reached. I'm going to add that little bit in here too. It doesn't matter if we actually get to that value, right? No matter how many 9s we put after the 0 here, we will never actually be at 1, right? Well, we could take a look at this sequence and things like this a little more, in much more detail in the Calculus 2 course. This is a single variable function here, this sequence, by the way, because there's only one input variable. The input variable is n, so it is a single variable function. Okay. So here's the idea of a limit. It's being approached by modifying the input value. We can get as close as we want to the limit by choosing an appropriate modification of the input value in the sequence. Okay. What is a derivative then? We're going to talk a lot about derivatives in this course. We're going to spend most of the semester talking about derivatives, how to find the derivative, how to calculate it, and certainly how to interpret it and how to apply it. Okay, how to do application problems, word problems by using derivatives. The derivative is an instantaneous rate of change. An instantaneous rate of change. Now, the geometric interpretation, that is, we can use geometry to analyze the derivative, right? We can interpret this derivative geometrically as, in fact, the slope of a line. We know the interpretation of slope from algebra. The interpretation of the slope of a line is rate of change. Well, the derivative is the instantaneous rate of change. It is dealing with, if we have a curve, what if we wanted to know, so a curve, the direction of travel keeps changing, so the slope keeps changing. What if we wanted to know what is the slope of the curve at a single point? What is the slope there? Okay, the slope of that line would be the instantaneous rate of change. All right, that is the interpretation of the derivative. And then later in the semester, we'll be talking about the integral. What is an integral? The integral is the sum of an infinite number of quantities, if that sum exists. Okay. So that's, if you were to add up a whole bunch of numbers, an infinite number of numbers, would that sum exist? Okay, would it be a finite number? Okay, take this example. What if we had the sequence, a very similar sequence to this, but a little bit different? What if I wanted to add together these numbers? 0.1 plus 0.01 plus 0.001 plus 0.0001 plus on and on and on. All of these numbers, let's note, all of these numbers are positive quantities. Okay, they're all positive numbers. Okay? And if we add up an infinite, and this is going to continue forever here, if we add together an infinite amount of positive numbers, we might suspect that adding together an infinite amount of positive numbers would always equal infinity. But in this case, that's not true. If we add it together, all of these numbers, we would get 0 point and a repeating 1 sequence. So 0.111111. Okay? And that is a rational number. It is a finite number, certainly. It doesn't go to infinity. Okay? And that finite number is 1/9 as a fraction. The sum of all these numbers. Now, this, in fact, is also called an infinite series. It's when you take all the numbers in an infinite sequence and you add them together. You get what's called an infinite series. And you'll talk about that in calculus too. But our interpretation of this geometrically in this course will be to use this, okay, to use this idea here of a sum of the infinite number of quantities in order to find out what is the area underneath a curve. So let's say we have a function, y equals f of x, and let's say it's bounded from a to b. What is the area of this region? It's an interesting question. Well, a way we can find it is if we can subdivide this region into a whole bunch of little, let's say, rectangles or trapezoids or parabolas, right? But we'll start with rectangles in this course. A whole bunch of really little sections. And then if we find the area of all of those geometric sections and add them all up, the sum of all those areas should be the same as the area under this region. Okay? And the integral will help us define that if it exists. So there's a lot of questions for us to answer here. Okay? These are the main concepts of calculus: sequence, limit, derivative, and integral. So calculus seeks to answer and interpret two fundamental questions, which are quite profound questions, and they are geometric questions. The first, what is the slope of a curve at a specified point? So like this one, we have to talk about the nature of the curve itself. It must be continuous, for instance. It can't have gaps in it, okay? And we'll see why that has to be the case as well, okay? What is the slope of a curve at a specified point is the first question that calculus tries to answer. And what is the area of a bounded region? And later we can even see what about an unbounded region, which you can look at in a Calculus 2 course. Okay, if that unbounded region is finite. Now, bounded geometrically in 2 dimensions means if you have a bounded region, it means that you can construct a circle with finite radius that would completely contain the region. That's bounded. Unbounded region would be if you have some shape that no matter how large of a circle you choose, so this continues outward forever, like this is unbounded, okay? No matter how large of a circle you choose, you would never be able to enclose the entire region. So that's the difference. We'll deal with bounded regions in this course when we get to dealing with the area problem. And the area problem will lead us right to integrals, okay? What is the slope of a curve at a specified point? And we want to interpret the answer to that question as well. Not just, this is the slope of a line, that's nice, but how do you interpret the slope of a line? And how do you interpret it within the context of that function? Okay. The first example of such we'll look at in an application sense in the very first section of this book, where we'll be dealing with a distance function. Okay. If you have distance as the output, and time as the input, okay, then the line, okay, then any line that you would choose, its slope, okay, would be a distance over time measurement, which is a speed or a velocity, okay, depending on its direction, it would be a velocity. The magnitude of a velocity would be the speed. So our interpretation of it, if we have distance versus time, could be velocity. Now, if the input wasn't time, let's say we weren't measuring time. Let's say it wasn't over time. Maybe it was over, maybe it was over a spatial variable, like the position. Let's say the output was something like air pressure. What is the air pressure? And let's say the input was altitude. In other words, at different altitudes above the surface of the Earth, as you change the altitude, as you increase in altitude, for example, or decrease in altitude, how does the air pressure change? All right, as the higher up that you get into the sky, the lower that the air pressure should be, because the force of gravity is pulling everything, including all the molecules floating around the gases in the air, pulling them towards the Earth. Okay, so it's more dense down here. There's higher pressure towards sea level. Okay. So you could say that the pressure changes as a function of the height. In other words, you could have the horizontal axis is a spatial variable, the height variable. Okay, so then when you're saying how does the pressure change, you're not answering a speed or velocity question, but you're still answering a question that has to do with how something is changing with respect to something else. Okay, so our interpretations of that slope. Okay. And the area, we'll deal with more interpretations of the area problem when we get to it. But I want to answer these questions right now in terms of calculus. What is the slope of a curve at a specified point? Okay. So the answer to question 1, the slope of a curve at a specified point, is going to be the derivative at that point. Okay, the derivative at that point. So let's say that point that we're interested in finding the slope for geometrically, let's say the input here is c. I'll use the variable c. Okay, so c is the x coordinate, if you will, of that point. Okay, in Newton's notation, the slope can be written as f prime of c. F prime of c. That is the first derivative of the function f of x, where it is evaluated at the input c, or f of t. Okay? Let's say that this is the function y equals f of t, because t is our variable for time in this case. Okay, so you would take the derivative of the function and input the value of the variable that tells you at what position you're interested in finding that slope. Okay, and the Leibniz notation would be to calculate the slope as a rate of change of the function. Okay, a rate of change of the function f. We're going to say df. Okay. So delta is used for difference, d can be used for difference, so a change. It is the change in the y value. Okay, you could also use y, dy, over dt. Okay, another way that we could write that, at that specified point, I'd want to maybe put a bar right here, okay, and write that t is equal to c. Or we could write dy dt, where t is equal to c. Okay, or we can separate out the operator, d over dt, saying we are finding the rate of change with respect to time, okay, of the function f of t, and then we're going to evaluate that at c. So Leibniz notation allows us to choose lots of different input variables. It is better suited when we have multivariable functions, and we should get used to the notation. Right? Newton's notation, this prime, assumes that we are taking a derivative whereby there is only one input variable that we could have chosen. There's only one thing that is varying within the domain. So the prime notation says whatever that thing is that's varying, that's the thing we're taking the derivative with respect to. So imagine if you had something that changed, a value that changed with respect to both time and distance, for example. Okay, with both time and distance. Then that measurement would be a function of both the variables time and distance. In that case, you could study how the output is changing with respect to time, and you could also study how it is changing with respect to distance. Okay, that would be a multivariable question. Okay, so the answer to question 1, what is the slope of a curve at a specified point? That answer is the derivative at that point. Okay, and the answer to question 2, what is the area of a bounded region? The answer to that is going to be the definite integral. Now, these two questions, geometric questions, okay, are interesting questions. They have a lot of applications, okay, but primarily they don't necessarily seem like they are related to each other. So if I take a curve, right? So if I take a curve and if I say I wonder what the slope is right here, that's a derivative question. And if I take the same curve and if I say I wonder what, if I find bounds here, I wonder what the area, okay, I wonder what the area of this region is down here. We're using the same curve, y equals f of x, but there doesn't necessarily seem to be a link between these two questions, okay, that we can seem to find by looking at it. And for a long time, it wasn't known whether there really was a link. Maybe there was, maybe there wasn't. But in fact, the two questions are related to each other. It is the processes that we use in order to find a derivative and to find an integral, okay? Those processes are inverse processes to each other. So the process we use in order to find an integral, if it exists, would be by locating, if we can find it, locating an antiderivative. Okay? So the inverse, the invertible process, okay, the invertible process which is used to relate derivatives to integrals, if they exist, okay, is called differentiation. Differentiation is the process. Okay? The inverse of that process is called anti-differentiation. So we'll be finding derivatives and we'll be finding antiderivatives. Okay. I'm going to take a look at an example of the limit of a sequence that I find to be an interesting one, where we can use analytical geometry to help understand this idea of limit of a sequence, right? Here we have a numerical representation of this. We have a bunch of numbers here. Okay. Here we have a symbolic interpretation of what we seem to be finding. Well, let's get a visual and a geometric one. And we're going to go back to the ancient Greek geometer Archimedes. And Archimedes found an estimate for pi by using polygons. Okay. So this is the approach that he took. He said, well, we already knew that pi is the, switch my layer. Okay, so pi is the ratio of the circumference of a circle to the diameter of a circle. Okay? So C is circumference, D is diameter. And so Archimedes would say, well, let's let the diameter just equal 1 unit, like 1 meter or 1 foot. Okay? And he was very meticulous about this. He would be very good at drawing circles and using a straight edge and everything. Okay? If you let D equal 1 unit, then the circumference of the circle, okay, then the circumference of the circle would exactly equal pi. So this circle, then, if its diameter is equal to 1 unit, then this circle has a perimeter or a circumference that is exactly equal to pi. And he said, well, I want to know what pi is exactly equal to, as precise as I can get. Okay, it turns out pi is an irrational number. You can never get the value of pi exactly. Okay, so you can only approach it. And he said, well, this is the approach that I'm going to take. I'm going to choose first. Well, here's how I can look at it. You can choose 4 points, for example, on the circle. Okay, and then you can connect those 4 points into a regular polygon. In this case, a square. That's if the 4 points are equally separated along the rim of the circle. All right. So if we did that, okay, we can then find the perimeter of our square. This would be the inscribed square, okay, it is on the interior of the circle, okay, and notice that the perimeter of the square is certainly going to be less than the perimeter of the circle. That is that the perimeter of the square is less than pi. It would have to be, all right? Well, the perimeter of the square comes out to 2 root 2. How do we know that? Well, we said that the diameter was going to equal 1 unit. So if this is equal to 1 unit and this is a square, use the Pythagorean theorem. With the Pythagorean theorem, we'll get that this side length and this side length each have to be, root 2 over 2. All right? Because 2x squared equal to 1 means x squared equals 1/2, and the square root of 1/2 is root 2 over 2. So we have the total perimeter of this inscribed square, right, is 4 times the square root of 2 over 2. In other words, 2 root 2. Okay, and as a decimal, that comes out to approximately 2.828427. Okay, that is less than pi, is the argument here. Geometrically, we can see that that's true. All right, so this number is less than pi. Now we can also take, using those same 4 points, we can create lines that are tangent to the circle. Tangent meaning that they only intersect with the curve locally at 1 point. And so they share the tangent line shares the same direction as the curve at that point. Okay? Tangent line. Okay? Tangent line shares a point and it shares the slope of the curve, okay, at that point. So this is a tangent line right here, right? It has the same slope and it has the same point as the circle for right there, and this is a tangent line right there, okay? All right, so we can find out what is the perimeter of this outer square. Well, this length right here is the same as this length right here. So we know that this length is 1, this is 1, this is 1, and this is 1. So the perimeter of the circumscribed square is simply 4 times 1, or 4. So he knows that C4, okay, the circumscribed square's perimeter is greater than pi. So now we have a bound. We know we have a lower and an upper bound. We know that, right? We know that pi is more than this 2.828427 number, and we know that it is less than 4, because 4 is C4. So we know that it is bounded between these two. He said, well, now I can take it a step further. I'm going to choose, at regular intervals along the circle, I can choose more points, and I can do an inscribed polygon and a circumscribed polygon. And in that way, as I increase the number of points, I can also approach from the inside and from the outside. I can approach the value pi as a limiting value of a sequence. Okay, and the numbers he chose started with the number 6, and he doubled it each time until he got to 96. He said, so here's an image of what it would look like to choose 6 equally spaced points. So we have hexagons. We have an inscribed hexagon, okay, a regular inscribed hexagon, which geometrically we can prove that the perimeter of that inscribed hexagon is 3, and clearly that is less than the circumference of the circle. So 3 is less than pi. And tangential line segments creating a circumscribed hexagon, okay, we can calculate that that's going to give us a perimeter of 3.46 approximately, so that must be more than pi. Okay, now double the number of sides by doubling the number of points or vertices here, okay, keeping that they are regular polygons that are inscribed and circumscribed. And what happens as we look at the numbers in the sequences that we've created here? Okay, we are the inscribed polygons, those values are increasing. They keep increasing, but they're not increasing to infinity, right? The inscribed, just because we have positive numbers that are getting larger and larger, that does not conclude that those numbers go to infinity. They could be approaching a ceiling, a finite value. And so we can take a look at the numbers, at the sequence from above, and see the reverse is happening. We have values that are getting smaller and smaller, but they're not going to 0, and they're not going to negative infinity. They are getting smaller and smaller to some finite non-zero number. And every step along the way, the actual value of pi is somewhere between the inscribed and the circumscribed values. For both of these sequences, this is I sub 6, I sub 12, I sub 24, I sub 48, I sub 96. Okay, the I sub n values are approaching pi. Okay, but all along the way, as I've written here, I sub n is always going to be less than pi. It's never going to reach pi. That's important. The value of a limit that we're talking about here, we're looking at the limit of a sequence. In fact, the limit of 2 sequences. Okay? The I sub n sequence is approaching pi. It never gets to pi. And the C sub n sequence approaches pi as well from above. Okay? But it also never gets to pi. This is a limiting process. He was doing this 250 years BCE. So well over 2,000 years ago. And this wasn't in context of calculus as we understand it today. Okay, but this is part of the roots of calculus itself. Okay, all right. So we're going to move on to the first section in the textbook, where we'll be dealing with the velocity problem. Okay, a velocity problem and the tangent. Okay, the tangent line, which I've already introduced here conceptually. What is a tangent line? Okay, to a curve. Okay, and going back to our questions of what are the main 2 questions calculus seeks to answer. Okay, the tangent line, right? The tangent line carries information for us about what is called the derivative, and it's an instantaneous rate of change. And as I've demonstrated here, if the function that we're trying to create tangent lines to, if that function is a function of time and the output is distance, then our interpretation of the derivative in that sense, that is the slope of this line, would be a distance over time. That is a velocity measure. So we already see using the geometry, right? We have an interpretation of the tangent line's slope, okay, as the velocity of an object when we are dealing with a position function. Okay, so that'll be coming up next.